Just 1 second. Okay, so let us talk about black body radiation. So today we're going to finish the program, and then in the last lecture we're going to I'm going to give you a simulation of what could be the final exam, and then send you all the how to say, all the various topics. I mean, all the various things that all the various texts of previous exams for previous years. All right, so black body radiation. So we're dealing with radiation, which is electromagnetic radiation. So I'm sure you haven't done this, but electromagnetic radiation can be described in quantum mechanics as having as a bunch of particles called photons, which have linear dispersion. C is the speed of light, and K is the momentum of the photons, and H is equal to sum over K and alpha. Alpha is the polarization of your photons, epsilon K, NK plus 1/2. All right. So what is, what is the physical content of this expression?
Sorry, what is N?
N is the occupation, of your photons. Is the number of operator, is A dagger K AK, where A is a creation and annihilation operator. So essentially, this expression tells you that photons can be thought of as a bunch of harmonic oscillators, right? Each one of them with a principal quantum number n, right? And n counts how many photons you have in each one of the modes. They're essentially like bosons, and they have an additional quantum number, which is the momentum of the photon. Okay? Of course, I cannot, this is something that I'm just writing. I cannot explain this. Explaining this formula would require to do a bit of quantum field theory, which is beyond the scope of these lectures. So, but I'm sure that all of you know that photons are bosons, and they have two polarizations. And they behave, well, probably you didn't know that you can write their Hamiltonian as in the form of a bunch of harmonic oscillators, but this is something I'm telling you. Okay? Now, in practice, what this Hamiltonian is telling you is that if you want the average energy, E of your photons, which is the average of H, well, this is going to be sum over the 0-point energy, sum over K and alpha epsilon of K over 2, plus sum over K and alpha of epsilon K and average N of K. And what is average N of K? Well, as I told you, we are dealing with bosons. And therefore, what we have is that this is sum over K and alpha epsilon K 1 over e to the h bar beta ck minus 1. Now, you should notice one thing here is that photons do not have a chemical potential. Why photons do not have a chemical potential? Because the number of photons are not like atoms. I mean, you don't create or annihilate atoms. The number of atoms is conserved. You have a certain number of atoms and that's it. And you fix the chemical potential at each temperature by the technique that I've shown you last time. Essentially, you require that the total number of atoms is equal to the sum over k of the Bose-Einstein distribution with the appropriate chemical potential, and you solve this equation for mu for each temperature. Instead, photons are completely different. So you can create and destroy photons at your as you want, right? In particular, here we will be trying to describe thermal radiation. What is thermal radiation? Thermal radiation is what happens when you take a cavity and you keep this cavity at some temperature, right? So what happens is that when you take this cavity and you keep it at some temperature, particular, the temperature is kept by essentially by the walls of the cavity. That could be, for example, a metal, like in your microwave oven, right? Or in an oven. I mean, a standard oven in which you cook stuff. When you close it, imagine as a metallic box, and you keep some temperature in it. What happens is that your walls start emitting and absorbing photons at some energy, which depends on the temperature. We're going to compute it today, how the dispersion looks like. But we'll essentially create and annihilate photons, absorb and emit radiation. So you should think of this process as something of this type. The walls will absorb and emit radiation. And this is going to happen with a certain balance. I mean, the entire system is going to be in equilibrium. But the number of photons that you create actually depends on the temperature, is not fixed, right? So you don't have a certain occupation of your photons. Photons are not like standard particles, can be created and annihilated. Their number is not conserved. So that's why I'm not putting here a chemical potential, because the chemical potential is the Lagrange multiplier connected to the conservation of a quantity, which is the number of particles. And here the number of particles is not conserved. Okay, so I hope it's clear to you that photons can be created and annihilated as you want, as you please. Okay. This is one of the characteristics of the, I mean, that's why I cannot actually demonstrate this formula to you easily, because this formula comes from a quantum field theory written up in second quantization. That is essentially the way to describe problems in quantum mechanics in which the number of elementary particles you're dealing with is not conserved. Okay. All right. So now,
Sorry, Professor.
yes.
I didn't see the relation why photons don't have chemical potential and
Well, because
no fixed number of.
So why do you need a chemical potential, right? A chemical potential is essentially connected to the fact that you. So how do you fix a chemical potential? You fix a chemical potential through this equation, right? 1 over e to the beta epsilon k minus mu minus 1, right? This is what we have done for Bose-Einstein condensation and company. But now what happens? What happens is that in the present system, the number of particles is actually not conserved. as you change the temperature, you continuously change the number of photons that the walls are emitting and absorbing in such a way as to maintain a certain equilibrium distribution in the cavity. Right? So that's why the chemical potential is not present, because the chemical potential is in practice a Lagrange multiplier that tells you what is how much energy, how much free energy you have to pay in order to create and annihilate particles. And this is not something that happens for photons. Okay?
But
it is needed for photons.
Professor,
Yes.
but actually, from your definition of chemical potential, you say that this is energy that we need to create a particle in your system. So in here, the particle is not conserved, so it's create or destroy. I mean, the number of particles changed. So as my logic, I think that it must have the chemical potential. So that's the reason why
What did you say? Sorry, can you repeat what you just said?
Yeah, what I said is that based on the definition of the chemical potential, it is the energy that we need to bring a particle into our system. So in here in our system with photon, we change the number of particles. So it means that we increase number of particles. So we need a energy to bring it in. So it's much related to the
but the point is that so no. When you change the number of particles, you pay both in internal energy and in chemical potential, right? Of course, as you increase the number of the occupation of your photon modes, the internal energy is increasing, right? As you see from this formula. So it's not that, but you don't have, the chemical potential is connected to the conservation of number of particles. Let me put it in a different way. How do you find that how do you determine the equilibrium between two volumes in a system, right? Two subvolumes, volume V1 and V2. If they can exchange number of particles, when do you have an equilibrium situation? You have an equilibrium situation when the two chemical potentials are identical. Why? Because when so this is a situation in which the total number of particles is fixed. The individual N1 and N2 can vary, and the equality of the chemical potential tells me, depending on the volume, how many particles I have in one and how many particles I have in two. So how am I distributing this total number of particles, N? Is it clear?
Yes.
Okay, so I have a big volume. I divide it into two parts. I can exchange number of particles. Here I have N1 and N2. And how do I fix N1 plus N2 is equal to a total N, right? So I have a conservation of a number of particles. And then how do I fix how many particles I have in one and two? The condition of equilibrium is that the two chemical potentials are equal. If I have the same species, of course, if I have different species and I have chemical reactions, it's a completely different story. Okay? What I'm saying is that for photons, the conservation of number of particles is absent. I can create photons and destroy photons as I want. And therefore, the condition of equilibrium is not determined by the equality of chemical potential, but is essentially determined by I mean, it's a special situation in which, as I increase the temperature, I can increase the occupation of my modes, of my photons, and the number of photons that I have in the system as I wish. You see?
Oh, yes.
Okay. All right. Okay, so given this first part.
Sorry, Professor.
Yes.
Do you want to just mean that we have mu if n is constant, is fixed, sorry? And
If the number of, so mu is formally, so in mathematical terms, mu is a Lagrange multiplier. I don't know if you know what is a Lagrange multiplier, but is essentially something that is connected to the conservation of the number of particles. It's called a Lagrange multiplier. You essentially fix it. If you have a certain number of particles, you fix mu in such a way as to conserve this number of particles. If you don't have conservation of number of particles, it doesn't make any sense to introduce a chemical potential. In a similar way, beta, the inverse temperature, is mathematically the Lagrange multiplier connected to the conservation of energy, right? So if you have a system, we never dealt with non-equilibrium systems, but if you would have a system that is out of equilibrium, and therefore in which energy is not conserved, then it doesn't make sense to talk about temperature. Temperature is something that is connected to the conservation of energy. In other words, if I take a system and I divide it into two parts and the total energy is conserved, E1 plus E2, how do I determine what is the condition of equilibrium and what is E1 and what is E2? I set the two temperatures, B1 equal to B2, right? The two temperatures to be equal. This is the condition of equilibrium, but the condition of equilibrium is connected to the fact that I'm conserving energy. If I would not be conserving energy, then it doesn't make any sense to talk about temperature. And if I'm not conserving the number of particles, it doesn't make sense to talk about chemical potential. Okay?
yes, okay.
All right, so now you see that there are two contributions. So the special thing about photons is that as you increase the temperature in a cavity, the number of photons in the cavity changes, the total number of photons, right? If I have low temperatures, as you can imagine, there will be fewer photons, and as you increase the temperature, there will be more and more and more. This is not something that you see with, if you would have infrared binoculars, like the ones they have in the army, and you would watch your oven, the one in which you cook, I don't know, meat. I'm sure that all of you have an oven at home. So if you watch your oven as you turn it on, and the temperature is kept at, I don't know, 150 degrees Celsius, with a microwave oven, you would see that the color is changing as you increase the temperature, change the temperature. Well, if you would measure the total energy that is sitting there, you would see that it's changing. The total occupation of photons is changing. Everything is changing, okay? It's a peculiarity of the electromagnetic field when you describe it as a set of particles. So the peculiarity is due to the fact that here we are trying to describe this phenomena from a quantum mechanical perspective. So in which the carriers of electromagnetic energy are some particles that are called photons. All right. So now, among these two contributions to the energy, this one is the one that is temperature dependent. So this is temperature dependent. This one, which is the 0-point contribution to the energy, is called the Casimir energy. Okay, it's actually a very interesting contribution to the energy because, in particular, it depends on what is the shape of your cavity. For example, if you take a cavity which is very long.
Sorry, Professor?
Yes?
Is Casimir a name of somebody?
Can I?
No. Casimir, what is the meaning?
Energy,
Oh,
Casimir. Casimir is the name of a guy.
Ah, okay.
Mr. Casimir. Okay, so if you take a cavity.
I'm so sorry, but what is the temperature so that we have Casimir energy?
No, the Casimir energy is the 0-point contribution. So it's this one. So you see it's temperature independent.
Oh, okay. Yeah.
It does not depend on temperature. It's there also at 0 temperature. And what I'm trying to say is that this 0-point energy actually depends on what is the shape of your cavity in which you put your photons, right? If you take a very long cavity like this one, is going to depend on the thickness of this cavity, on L. And in particular, as you increase L, what you would see is that as you increase L, what you would see is that this Casimir energy changes, but an energy that changes with L means that if you take a derivative, you have a force that keeps essentially that is mediated by the electromagnetic field between these two plates as you try to move them far apart. And this force is called the Casimir force. Anyway, this is a completely different topic. Let us keep it as a general discussion and let's forget about it now. So I'm not going to deal with the Casimir energy and what I'm going to say next. So let me forget about the Casimir energy and subtract it. So let me consider E minus E Casimir. And passing to the, so this is sum over K and alpha, epsilon K, 1 over E to the beta, H bar CK minus 1. And then this is equal to 2, because I have 2 polarizations for my photons. Then I have V over 2 pi cube. And then I have integral dk of epsilon k divided by e to the beta h bar c k minus 1. Okay? So now I can pass to the spherical coordinates because my dispersion is actually dependent only on the absolute value. So we'll have 2v over 2 pi cube, and then 4 pi, the solid angle, integral dk between 0 and plus infinity, and then h bar c k times k squared divided by e to the beta h bar ck minus 1. All right, so now I can easily calculate this integral by setting beta h bar c and k equal to x. So I change variables.
Sorry, Professor.
Yes.
True polarization for photon means what?
Well, yeah, that's something that you know that that photons are is a purely transverse wave, right?
Yeah.
So which means that you cannot have. So if if you have a photon that is moving in this direction, unlike sound waves, you can the oscillation happens only in the transverse direction. So either along this direction or along that direction. You cannot have a compression wave for photons in which the oscillation happens in the same direction as the propagation. So if I have a certain momentum, then I have only two possible directions of oscillation, which means that it's a purely transverse wave, and that's it. I have two polarizations.
Okay, thank you.
If you know, that's why you can have Polaroid glasses. You know that you can. There are certain types of glasses that actually block photons or electromagnetic waves with a certain polarization, let through only a given polarization. And in particular, you can convince yourself with two Polaroid glasses that photons are transversely polarized if you take one that is polarized along one direction, the other one that is polarized in the opposite direction, you will see dark. Okay? So anyway, these are basic facts about electromagnetic radiation. All right, so now I change variables. What do I get? I get V over pi squared. And then I get 1 over h bar c cube beta to the fourth, and then integral between 0 and plus infinity dx x cube divided by e to the x minus 1. This is the same integral they encountered last time, right? We know what it gives. So it gives v over pi squared. And then I have kbt over h bar c to the power 4 times h bar c times zeta 4 gamma 4. So if you now go to the tables and look at what is the value of gamma 4 and zeta 4, believe me that at the end of the day, you will get pi squared over 15 times v times h bar c times kbt over h bar c to the power 4. So this is the average energy. Okay? Now, do you find this surprising? Well, so let me skip this rhetorical question. So the issue is the following. It was known already to, this problem of black body radiation was actually one of the most important problems that led to the discovery of quantum mechanics. Why? Because it was known that you could see the electromagnetic waves as a bunch of harmonic oscillators, even classically. And what was also known was that there is something called the Equipartition Theorem, right? The Equipartition Theorem would tell you that the electromagnetic radiation, the average electromagnetic radiation at some given temperature T is going to be, for each mode, you're going to get a contribution to the energy, which is kBt, essentially. Okay? Actually, you have two polarizations, so you're going to have 2 kBt. So for each one of them, kBt, and then a factor of 2 for the polarizations. Never mind, it's going to be linear in the temperature. And instead, this result, which was also observed experimentally, is not linear. So this was surprising. Something that was unexpected and cannot be explained, or is a discrepancy between quantum statistical mechanics and classical statistical mechanics. It's essentially the observation of something that does not fit in the standard equipartition theorem. So it's something that led people to think about what could be the possible reason and what led
Professor,
Mr. Yes.
What's the thing that is unexpected?
Well, so if photons were classical oscillators, then the equipartition theorem would imply that the average energy per mode is kBt, right?
Right.
And instead here you see something that is not linear, is a t to the 4th. So it's surprising, does not fit what we know about what was known in the context of classical statistical mechanics. Now, how would you measure this black body radiation? So I told you it's essentially the radiation that happens if I have a cavity at some given temperature. So a cavity at some given temperature is a black body. Black body because all the radiation is contained inside the cavity, right? And is continuously absorbed and emitted by the walls and doesn't get out, in a sense. It gets out if I make a little hole in my black body. So how would I compute, how would I measure this radiation in practice? Well, one thing I can do is take the cavity, make a little hole here, and then measure the radiation that gets out of this hole and the flux of radiation that gets out of this hole. Now, if you take a balloon, right, like the ones you have seen when you were kids, and you make a hole in it, well, the balloon is going to start to deflate, and the flux of air that gets out is going to be proportional to the pressure that you have inside the balloon, right? So the higher the pressure, the more flux of air you will get out of the hole that you pinch on your balloon. So in order to compute the flux in this case, we have to compute therefore the pressure that the photons are exerting on the walls, okay? And the pressure, P, we know is given by minus dF dV, where F is the Helmholtz free energy. So what is the Helmholtz free energy in this case? Well, it's essentially the Helmholtz free energy of a bunch of bosons without a chemical potential, right? So with mu equals 0. So the Helmholtz free energy is going to be given by 2V kBt times, I'm passing immediately from summation to integration, integral dk over 2 pi cube, and then as we have done a few lectures ago, e to the beta c k minus 1. Okay, so this is the Helmholtz free energy. All right. So now the pressure, therefore, is going to be equal to what? To the derivative of this with respect to the volume minus, which is minus 2. And then I have integral between under dk 2 pi cube log of e to the beta ck. I'm setting h bar equal 1 in this formula, times this times kBt. All right. So now it's convenient to rewrite this log as log of e to the beta ck times 1 minus e to the minus beta ck, which is equal to beta c absolute value of k plus log of 1 minus e to the minus beta ck. Okay? Now, if I substitute this expression in here, I get a first contribution, which is minus 2 integral dk over 2 pi cube. And then I have kBt times beta ck. And then I will have minus 2 integral dk over 2 pi cube kBt times log of 1 minus e to the minus beta ck. Okay? All right, so now this goes with that, and therefore we see that this first contribution is temperature independent. So let's call this P naught, temperature independent. And the second one instead is temperature dependent. I can change variables, set beta c absolute value of k equal to x, pass to spherical coordinates, in which case this is 4 pi times dk k squared, and do the same things we have done 2,000 times. In this
Anyway,
lecture,
hold on,
yes,
please. A moment, okay.
yes. Can I move on?
Yeah.
Just a second.
Yes.
Professor,
Yes.
what is
moving.
P naught? Is it
P naught is
if
just a contribution to the pressure that is temperature independent.
so it depends on something else like
Well, it depends on the size of your cavity. It's like the Casimir energy. It's
okay.
independent on temperature. So it's just sitting there. Depends on the size of your cavity, how it looks like.
Is it
Not to-
similar to the, atmospheric pressure?
Well, the atmospheric pressure depends on temperature. Believe me.
Well, I mean, in the context that it does not depend on height. I don't know.
No. It depends. No. It's not the same. It's actually very peculiar because this is okay. It depends only on the shape of your cavity, nothing else. Anyway, can I go on?
Yes.
Okay. So now you do this change of variables, everything as I said, and you will get P naught minus KBT over pi squared. And then from the change of variables, you will get KBT over C cube. And then integral between 0 and plus infinity dx x squared log of 1 minus e to the minus x. Okay? Now, this integral is an integral that can be done by parts. So it's integral between 0 and plus infinity dx x squared log of 1 minus e to the minus x. This is x cubed over 3 times log of 1 minus e to the minus x between 0 and plus infinity minus the integral between 0 and plus infinity dx x cubed over e to the x minus 1 over 3. So I'm evaluating this integral by parts. And then, well, so this one is 0, and here from this I get minus, I get the zeta for 1/3 times, so this is equal to 1/3 zeta 4 gamma 4. And therefore, I substitute up there, I look at the values of zeta 4 and gamma 4, and I get that this is equal to P naught plus 1/3 pi squared over 15, then C, and then KBT. Well, let me put back H bar. KBT, H bar C to the 4th. So this is essentially P naught plus 1/3 the energy density that we calculated before divided by V, E of T divided by V. Okay, so this is the pressure. So what is going to be the total flux of energy they get if this is the pressure inside my system? Well, you see, if I pinch a hole, not all the particles so if all the particles have an absolute value of velocity equal to c, the speed of light, not all the particles that come to this wall, that are close to this wall, can get out, right? Because this is outside and this is inside. Only particles which have a projection of the velocity in the, let's say this one is the x direction, in the x direction that is positive, right? Only these particles can get out. So therefore, what I have to do is when I have to essentially compute, and when they get out essentially with this velocity, with the projected velocity in the perpendicular direction. So what I have to do in practice then is, for all these particles,
Sorry,
which have, yes?
Can you repeat this?
I'm just saying this. Suppose that you have, so any particle that is coming out with a velocity pointing in this direction, right? If this hole is infinitely small. And what is this velocity? This velocity is the projection of the velocity of the particle in the perpendicular direction. So if you have a photon that is impinging with this momentum, you just project this velocity vector in this direction and it will get out with this average velocity, right? So therefore, if I want to estimate the flux that gets out from this hole, so it's essentially the energy per unit area and per unit time, what I do is multiply the energy density by the average velocity in the perpendicular direction. And the average velocity in the perpendicular direction is c integral over the solid angle divided by 4 pi of n of the photon, the direction of the momentum of the velocity vector of the photon projected on a perpendicular. Here I'm not integrating over the entire solid angle, I'm integrating only over the portion of the solid angle which has a positive projection. So it's this one, right? So n omega plus. Well, if you do this integral, you will get that this is nothing but c over 4. You get a factor of 4.
I'm so sorry, but
Yes.
I don't get the part that it will move. I mean, it will, like the velocity will be projected in x direction, because I'm thinking of the phenomena when we have diffraction. So when we have photon go through a small split hole, and then it's diffract, and it's in many direction. I mean, in all direction. So what in this case, it's just in x direction.
Well, so what happens if the size of your hole is infinitely small to your diffraction?
I think that it's act as a obstacle and bend the wave.
Look, so to be honest with you, I would need to think about this at the moment. So I don't remember in which limit. So your question is a good question in the sense that there is a limit on the size of the hole as compared to the wavelength of the radiation in which this is correct. And you're asking me in which limit am I putting myself? I don't remember. So let me postpone this question. So let me say that there is a limit in which all this calculation is correct. It doesn't really matter for what I'm going to say in a second. Yes. But in practice, so and then I will specify next time which limit. So what is the what has to be the wavelength of the radiation as compared to the physical size of the hole?
Yes.
Anyway, whatever is this, so what I'm trying to compute, whatever is this factor for whatever, what I'm trying to say is the following. If you want to compute the flux of radiation from the hole, even dimensionally, this is going to be an energy density times a velocity, right? Times c times a prefactor. I'm claiming this prefactor is 1 over 4. So in practice, therefore, what experimentalists measure is this flux, energy density per unit, energy per unit area per unit time, okay? Which is c over 4 E over V, and is equal to pi squared over 60 times KB4 divided by h bar cubed C squared times T to the 4th. Okay? So now this constant here has a name, is called the Stefan constant. So anyway, all of this confused explanation just to say the following. If you have a certain energy flux, a certain energy density in your system, then you can imagine that this energy density will exert some pressure on the walls. If you make a tiny pinch, so drill a little hole on the walls, radiation will start getting out. And how it will get out? What you will see is essentially the energy density of your radiation So what you will see is essentially per unit time is the energy density of the radiation that stays in on this side of the wall and that gets out, right? So the energy per unit, the flux per unit area, so the energy per unit area and per unit time is going to be given by this expression. All right. Now, yes?
Sorry. I have a question. Can you go back to the previous one?
Mm-hmm.
So this what's the factor n here? N photon and n perpendicular.
N photon is the direction of the versor for the photon, of the velocity versor of the photon. N perpendicular is the versor that is perpendicular to the direction of the surface.
Do you have the magnitude? Like, I mean, this will result in cosine, right? And then you will integrate over the.
Yeah. This is just yeah. So I mean, calculation of this is you will get a factor of 2 pi, and then integration between no, actually it's not 2 pi, a factor of pi. And then so you have to integrate over half of a solid angle. So integral between 0 and pi d theta of sin theta. And then from this projection, we'll get cos theta. And then you have to divide all of this by 4 pi.
Okay.
Okay, so this is the integral.
I mean, you don't have the amplitude of n photon.
I don't have what?
So this is unit vector.
Yeah, it's a unit vector. Is a unit vector, yes.
What about this expression E energy of the function of temperature divided by volume? I mean, I don't see the volume here.
What is this? What? Sorry, what? Which expression?
The P0 plus 1/3 E function of T.
Well,
over.
so this expression was just to show you that I have a certain pressure that is being exerted on the walls. So now below here, I'm computing what is the flux that I will see getting out. That is also temperature dependence. And I'm claiming this flux is essentially coming from, so suppose that I drill a hole, I have to estimate what is per unit area. So here I have a certain area, and per unit time, right? What is the energy density that is sitting in here, in this little cylinder?
So what I mean is, I don't see where is the volume expression from the previous expressions. I'm not
I
sure
don't understand your question. What is where is the volume expression in which sense?
in which sense. How do you get V? What's
Oh,
V?
actually, now I realize that the answer also to the question by Lynn. So what I'm trying to see in this second, so I'm drilling a hole, right? So this is supposed to be the hole. Let me do it properly. So this is my surface, and I'm drilling a hole, and I'm looking at the radiation that comes out, and I want to estimate the flux. All right. So the flux is energy per unit area per unit time. Okay. So now the question is how much. So I imagine that there is an energy. I mean, a certain per unit time, I have essentially a cylinder of radiation that gets out of this wall, right?
Yes.
And now I want to estimate how much energy is sitting in here and then divide by the area, etc., etc. How do I do that? Well, I essentially have to estimate what is the height of this cylinder. And the way I estimate what is the height of this cylinder is by estimating what is the average velocity of a photon in the perpendicular direction when it's getting out of the hole. So in practice, I'm taking all the photons that are impinging on this guy, and I'm computing the projection in this direction and averaging over all possible directions. This is, in practice, the average velocity of a photon that is perpendicular in the direction perpendicular to the surface. Okay? And I'm saying this average velocity of a photon is c/4, right? So now, suppose that I now want to estimate what is the flux. How do I do that? I take the density, the energy density, so E/4. Then I multiply by the volume of this cylinder. The volume of this cylinder is what? Is C/4 times the time. Sorry, suppose that I want to estimate not the flux. I want to estimate how much energy gets out of my hole in a unit time delta T if the hole has an area A. So this is given by the average velocity in the perpendicular direction times delta T. So this is H. Okay? Times the area, and this is the volume of the cylinder, times the energy density, right? The energy density of my radiation, which is E/V. Okay? But now I don't want the energy that gets out. I want the energy per unit area and per unit time, the flux. So this is given by E delta T A divided by delta T and A itself. So therefore, this is equal to average C perpendicular E/V, and average C perpendicular is C/4 E/V. Is it more clear now? Is it better? Did you get the logic of this calculation? Hello?
Yes, I think.
Lynn,
Yes.
is it okay now? Did you get the logic?
Yes.
Okay, good.
Mm,
Okay, so just a second. Now, okay, so this is the Stefan constant, T to the fourth. Okay, so in practice, if you're an experimentalist, you would measure this energy density by drilling a hole and looking at the temperature dependence of the total energy that comes out of your hole. This is the black body radiation, temperature dependence of the black body radiation. Now, another thing you could think of doing is not only measuring the flux, but measuring the flux, looking at, selecting also the frequency of the radiation that gets out. In other words, doing a spectrally resolved calculation. Okay, so how would I do that? Well, what I have to do is I have to remember that E over V is actually equal to 1 over pi squared, and then I have integral 0 and plus infinity decay decay h bar c k cube divided by e to the beta h bar ck minus 1. So I can see this as the integral over decay of the energy density of radiation with momentum k. The momentum is 2 pi over the wavelength. Okay, so this is a wavelength resolved quantity at temperature T. And given this expression, I could predict that the flux, actually, phi of radiation with wavelength lambda and at temperature T is going to be given by C over 4 epsilon 2 pi over lambda times NT, where T is the temperature.
what's that in the, sorry, N or K?
What is
Yeah, what do you want to write there?
lambda? Okay. So now, if I look at how this flux looks like as a function of the momentum of the radiation, I'm going to see something of this type. So this is phi of k. K is 2 pi over lambda versus k. I'm going to see something that does this and then decays exponentially and has a maximum at a momentum which is equal to kBt over h bar c. So this is another peculiarity of electromagnetic radiation when it is considered as a quantum mechanical origin. So this form is actually demonstrating, in a sense, that electromagnetic radiation is quantized and is something that was used historically to introduce photons as the quanta of electromagnetic radiation. All right, so now let me very briefly tell you what happens for solids, for a different type of excitation that occurs in solids, the phonons. Now, you all know that phonons are, that vibrations in solids can be described by a bunch of harmonic oscillators. You've done phonons in quantum mechanics, right?
In solid state physics.
In solid state, excellent. So you have done phonons, you know what phonons are. And in particular, you know that the Hamiltonian that describes the vibrations of a lattice in a solid is sum over k and alpha omega k nk plus nk and alpha plus 1/2. Again, it's a bunch of harmonic oscillators. The difference between phonons and photons is that phonons can have tripolarizations. So there are two types of transverse phonons and one longitudinal phonon, which is the sound mode, the standard sound compression mode. And typically the dispersion at low energies, if you don't have peculiar behavior like 2 atoms per unit cell, in which case you will have also optical phonons, is that of a sound wave. So you will have C times K, absolute value of K, right? So this is the typical phononic dispersion where C is the speed of sound. Therefore, not surprisingly, if we compute for phonons the average energy, U, what we are going to get is that the average energy is equal to, I'm just rewriting formulas that I already wrote for photons, 3 times kb t to the 4th divided by 2 pi squared c cubed times v times the integral in dx. Just a second. Pronto? Buongiorno. Sorry, guys, I had to answer a phone call. Can you still see the screen?
Yes.
Okay, so I was writing dx x cubed e to the x minus 1. So the story is exactly the same as for photons, with one little difference. When you have photons, you are dealing with a field that essentially comes from the electromagnetic field that is defined in a continuum space. Instead, for photons, the total number of for each momentum, the total number of modes that you can have is fixed and is given by the total number of atoms in your solid. In other words, if I sum over all possible momenta 1, I should get that this is equal to the total number of particles. Okay? The total number of allowed momenta that describe your photons has to be equal to the total number of, has to be equal to the total number of particles in the solid. Now, this tells me, therefore, that this integral here that I wrote up here, unlike for the case of photons, cannot be between the limits 0 and plus infinity. This would not make sense, because if I would take it between the limits of 0 and plus infinity and would do the same in passing to the integral here, so v over 2 pi cube, solid angle, integral 0 and plus infinity, dk, k squared, I would never be able to satisfy this constraint. I have to put an upper cutoff in this integral. And the upper cutoff is essentially beta times a frequency that has to be fixed by the condition below this one. K d by has to be fixed by the fact that I set this equal to the number of particles. This frequency is called the dBi frequency, and this momentum is the dBi momentum. The two are related by omega d equal to c times kd, where c is the speed of sound in my system. All right, so let's see how to write down the dBi frequency as a function of the density in my solid. It's actually quite simple. I can just make a change of variables here and define omega as c times k, in which case I get that this integral can be written as v over 2 pi cube times 4 pi over c cube, and then integral between 0 and omega dBi d omega squared, and this is equal to v over 2 pi squared times c cube times omega dBi cube over 3. And this has to be equal to n. Therefore, I see that this cutoff, the dBi frequency, has to be equal to c times 6 pi squared rho is the density, n over v, to the power 1/3. Okay? Therefore, the average energy, now if I take this expression and I consider the fact that I have an upper cutoff in here, this tells me that the average energy, E over per number of particle, is equal to, is not proportional just to temperature to the 4th power. So it's not a function that does this, and that's it. Because there is also some temperature dependence that is inherited from this cutoff and from this peculiarity of phonons as compared to photons from the dBi frequency, right? There is a temperature dependence sitting in here. This temperature dependence, I can isolate it by rewriting the energy density U over N as follows. U over N as 3 kBt times 3 over kBt integral between 0 and beta omega d dx x cubed over e to the x minus 1. And this is called the Debye function. So this is another peculiarity of d of beta omega d. So it's a function of the ratio between the Debye frequency and the temperature. Now, this peculiarity, the fact that you have a temperature dependence in here as well, by the way, here there is a cube, I forgot it, is actually what leads to the fact that if you take a derivative of the internal energy with respect to temperature that gives you a specific heat, you will get something that looks like this. Something that grows like T cube and then eventually saturates. So it grows and then saturates. And this growth at small temperatures of C over NKB as T cube is actually characteristic of the quantum mechanical behavior of solids, of phonons in solids. Of course, when the temperature is very large, the specific heat actually is what you get from Equipartition Theorem, and therefore this quantity here will saturate to 3. But at small temperatures, you will see deviations. So this story here are deviations from equipartition, which are due to quantum mechanics. Okay? All right. So I'm essentially done for today. Do you have any questions? Are you still there?
Yes.
Yes, sir.
Do you have questions?
I have a question.
Yes.
I did not get you clearly when you were talking about the phonon modes, how you were trying to relate it with the photons, and also how you changed the, how you had to put in that upper limit from infinity to the Debye frequency.
So, well, unfortunately today, I mean, you know, I would go slower on this and redo the calculations of phonons, but just to explain this point, but I hope you know from solid state that when you deal with phonons, right, which have a dispersion epsilon of k, the number of modes, right? So this dispersion is defined on a k that is defined on what is known as the first Brillouin zone. Did you know this? Did you ever hear this name? First
Yes.
Brillouin zone, right? So what is the first Brillouin zone? Is essentially counting how many k's you can have that fill that. So the total number of momenta that are allowed, that are sitting in the first Brillouin zone, is equal to the total number. No, sorry, I'm getting confused. Just a second. No, it's correct what I was saying. So the total number of momenta that sit in the first Brillouin zone is given by the constraint that the total, the number of states in the first Brillouin zone has to saturate the total number of particles in the system. Okay?
Mm-hmm.
So that you know from solid state physics.
Yes.
So what I'm saying here is the following. Here I'm using the usual trick. In principle, when I compute the average energy, I should write down a sum over K of, so internal energy should be sum over K and alpha, omega K, average and K, right? This should be the internal energy. It should be a discrete sum over the discrete momenta that sit in the first Brillouin zone, correct?
Yes.
However, I typically forget about this and I write it down as a continuous integral, right? That's what I did for phonons. Phonons do not have a first Brillouin zone. Photons, sorry. So I can transform this into an integral. The problem is that when I transform it into an integral, since I do have a Brillouin zone, I have to put a cutoff in here. And how do I set this cutoff? I set it by imposing exactly this condition. Okay?
Okay.
That the total number of Ks in the first Brillouin zone is equal to M. And then this condition essentially, if I transform this sum into an integral, gives me omega d as a function of the density. Okay?
So you mean when we sum up to infinity, we cannot get the...
No, of course you cannot, because if you sum up to infinity, how many modes are up to infinity? Infinity, but this is not good. So this is not what you do in solid state physics, right? In the
Yes.
first Brillouin zone, there is only a limited number of Ks. Not all Ks can be taken. Only the
Okay.
ones in the first Brillouin zone. All right?
Okay, thank you.
Other questions? Okay, so if no other questions, then next time you will be using your wonderful new laptops and we'll be doing some exercises. Hopefully everybody will have a laptop by then. Otherwise, well, we will operate in an interactive mode, okay? So I'll see you on Tuesday.
Bye.
Bye. Bye-bye.
Goodbye.